Hi, good morning. Let's continue our topic for this week with engineering applications of integral. So at the end of this week, you should be able to do these following applications for integral, for engineering application. So we're going to cover the arc length, the area of surface of revolution, hydrostatic pressure and force. And in the hydrostatic pressure and force, we're going to see the pressure on a vertical surface instead of a horizontal surface. And finally, moments and centers of mass, where we're going to cover the centroid of a plane and the theorem of Pepper's. So just a take note here that we cannot cover all engineering applications now, since you are still in first year. You've only been here for 7 weeks tentatively for academic calendar, and you have not covered a lot of engineering elements in your respective programs. So what we're going to cover here in engineering applications are broad engineering applications, which maybe you can relate from your previous experience in physics, right? Okay, so let's first go through the first application, which is arc length. Okay, let's say you have a curve. Okay, so how would you measure the length of a curve? You can intuitively, let's say you take a piece of string and then you fit on the curve here. Okay, you take a piece of string and then you fit on this curve, and then and you mark the beginning and the end of the measurement. Then you take out the curve. You take the curve and measure the length from the starting point to the ending point with a ruler, and then you measure and you take the length in cm or in whatever unit that you are given. Okay, so that is how we would intuitively measure the length of this curve. But that might be difficult to do with a high accuracy if you have a more complicated curve. So just like the concepts of area and of volume, we need a precise definition for the length of a curve. For example, if you have an area under the curve, you can do an integration from the beginning to the end of the curve limits. But we should have something like that for the length of an arc curve. Okay, let's say if the curve is a polygon. So if your curve here is polygon, so let's say so this is your y-axis and this is your x-axis. So let's say your curve look like this. It consists of a polygon. Okay, so you can easily find the length of this curve by just measuring the length of this line plus with the length of this line plus the length of this line, and so on. You can go on and on until you reach the end of the point that you want to do the measurement. You just add the length of the line segments that form the polygon. So you can use the distance formula to find out what is the length of the polygon. So let's say this is the x value, let's say x1, and then this will give you y1, and then this is your x2, and that will give you y2. So this is 0.1 and this is 0.2. So if you want to find the length of 0.1 to 0.2, P1, P2, all you have to do is to measure the length from P1 and P2, and this one you can use a theorem of Pythagoras theorem, to calculate the hypotenuse. Okay, you calculate this length by measuring the delta y and measuring the delta x. So you get the square root of y2 minus y1 plus x2 minus x1, then you get the length of P1, P2. And so if you want to measure the length from P2 to P3, you would repeat the same thing, and P3 to P4, and so on until Pn, right? And Pn and Pn minus 1, for example. Okay, so it's easier to find the length of a curve if it consists of a polygon. You can also imagine the same thing if you have a circle, for example. Let's say you have a circle. So you can divide this circle. Mine is not a very nice circle, but you can see that it's a circle. So let's say if you divide this circle into the different segments of polygon. So let's say if you divide it into 4 segments, right? So you may want to approximate the length of this circle by approximating the length of each side of the polygon. In this case, the polygon is a square, so you want to measure the length of side 1, side 2, side 3, and side 4. It would be more accurate if your polygon, if the polygon that you are dissecting the circle with is broken down into more shorter segments. Okay, so if you have this circle, and this time you want to divide it into, let's say, hexagons. So 1, 2, 3, 4, 5, 6 sides of a hexagon. So you can approximate the length by measuring the length of the circle here. You want to measure, then you can approximate it by approximating the length of the hexagon. And it would be more and more accurate if you divide the circle into smaller length of polygon, like a polygon with more sides. And the smaller the segments, the more accurate is your measurement of the circumference of the circle. So we can do something like that to approximate the arc length, i.e. the length of a curve. So you may want to, divide this curve into smaller segments of polygon. Then you want to measure the length of the small segments of polygon, and you add them up, and then you get the length of the curve. Okay, building on from that concept, so you can imagine, or not imagine, like if you are given a curve, so this is your y-axis and then this is your x-axis. So let's say you have this curve, okay, and you want to find the length of this curve starting from, this is your limits for the curve. So this function is just this curve is built by the function y equals to fx. Okay, so you can first intuitively, from that concept of dividing the curve into different segments of straight line, so that you can measure the length of the straight line more easily. So from A to B, you may want to cut this distance from A to B into half, and then further into smaller halves. When the point here is you want to divide the length of A to B into segments of same length, delta x of same length. Okay, I'm not going to divide it into too much smaller segments, because otherwise it's difficult for you to see, but we can start here. Okay, so let's say this is your starting point, x0. Then this one is x1, x2, x3, so on and so on, and there will be xi minus 1, xi, and finally at x equals to b, this would be your xn, noting that this is your final segment because you're dividing into n number of segments. So this is your xn, and then this is your p0, p1, p2, p3, and so on until pi minus 1 and pi, until you get to the pn at the end of the curve. Okay, so you can draw the lines connecting all these points. Okay, connecting all these points. So from p0 to p1 you get one line, p1 to p2 you get one line, straight lines. Okay, so you can just continue on to just approximate the length of this curve by approximating using the line of the segments. So from here you can measure the length of from point 0 to point 1. For example, let's take this from PO P1 plus P1 P2 plus P2 P3 plus so on and so on until Pi minus 1 to Pi, and so on until Pn minus 1 to Pn. This, if you add these all together, will give you the total length of the curve from x equals to a to x equals to b, and you can write it down in the summation formation as the summation of the modulus of pi minus 1 to pi, where I starts from 1 until I equals to n. So the length would be more accurate if n approaches infinity. You know, like if you have more number of n's, then your division of segments will be smaller and smaller. And we talk about this, that if you divide the curve into smaller segments of polygon, then your approximation of the length would be more accurate. So you can write down the length, the total length of the curve equals to, you take a limit as n approaches infinity, and summation from I equals to 1 until I equals to n, from pi minus 1 to pi. So this is where we are starting to find the formula for the arc length function. However, this term here is not very useful for computational purpose because it's written in terms of limit and in summation function, and we don't really have a formula, a discrete or analytical formula to find out what is the length from pi minus 1 to pi. So we need to convert this term. Okay, so let's take one point from pi minus 1 to pi. Okay, continue here. So pi minus 1 to pi, any point here. Okay, so just look at the curve again. So we are focusing here, right? So you can take this, the length here is what we would measure, the delta y, and here is the delta x. So the delta y is yi minus 1 squared plus xi minus 1 squared, the whole thing squared. Okay, it's just a Pythagoras theorem. Okay, take note here that the delta x is constant because we decide to divide the delta x we decide to divide the intervals from a to b into similar lengths of delta x. Okay, we want to divide it into, delta x is constant, it's of the same length, but delta y is not. Delta y is not constant because if you can see here from this curve that it's just different. You cannot assume it's constant. The point, the delta y changes as point move to one point, move to the other. For example, from P3 to this point here, it's longer compared to P1 and P0. So you can write this down. So, okay, delta x is constant, but delta yi is not. Okay, you can write it down as delta yi squared plus delta x. So since delta x is constant, you don't need to write it down as delta xi because it's the same. Delta xi or delta x minus 1, I minus 1, then you don't need to do anything about it. So now here we're going to continue to use the mean value theorem. Okay, before we proceed to apply the mean value theorem, if you need to further understand the concept of mean value theorem, please refer to this YouTube video that I attach here. Okay, so you can either type down the link and go to your browser, YouTube or whatever, or you can just scan this QR code here and it will bring you straight to the video I'm talking about for you to understand better on the mean value theorem. So let's just proceed to use the definition of mean value theorem. So basically, mean value theorem says that, okay, let's say you have this small curve here, right? Okay, let's say you have this value xi minus 1 and this is xi. So in the middle somewhere here, you can put it as xi star, okay, xi star. So basically, mean value theorem tells you that the derivative of fx at x equals to xi star is equal to delta yi over delta xi. So delta yi would be, this is your yi minus 1 and this is your yi. So this is your delta yi, and this is your delta xi. Okay, so mean value theorem gives you the relationship between the derivative of f, so fx prime at x equal to xi star equal to the delta yi over delta xi. So what we can do here is that, okay, from previous slide we have this pi minus 1 pi equal to delta x squared plus delta yi squared. So we're going to use this definition of mean value theorem to substitute into this formula. So from the mean value theorem, we have this delta yi equal to f prime xi star delta x, and we're going to put that inside here. Thus, pi minus 1 pi equal to delta x squared plus f prime xi star delta x, everything here is squared. Okay, from here you can factorize the delta x. So delta x, you take it out, and then square plus 1 plus fix, oh sorry, xi star delta x, everything is squared as well. No, okay, it's just that thing. Then you can take out the delta x, so you have 1 plus f of x I, sorry, I screw up here. So okay, so here is squared. Okay, then we take out the delta x because square root of something squared is just that something. So you can write down this pi minus 1 pi is 1 plus f prime xi star, the whole thing here squared, delta x. Okay, and previously this is for just one length. Okay, so previously we have the definition of L equal to the limit from as n approaches infinity, okay, the summation of pi minus 1 to pi from I equals to 1 to I equals to n. Right, so we can substitute this with what we have derived earlier. So you can just rewrite this formula as this one. Just I'm substituting this thing here, 1 plus f prime xi star, everything here is squared, delta x. Okay, right, so I know that based on the mean value theorem just now that fxi prime is delta yi over delta x, and that this xi star here, it lies between the value of xi and xi minus 1 and xi, you know, like xi star is in the middle of these two values. But when you divide the length AB into very small segments, okay, like very small segments, so this is just a magnification of your division. So here is your xi star, so you can approximate this f of xi star to be about the same with f prime xi and about the same with f prime I minus 1, because actually the value from here to here and what in the middle here is very close. So then you can convert this notation in terms of limit to a more useful notation, where originally you have the limits from A to B in your curve. So you can just transform this value inside there with just f prime x, everything squared, and the delta x here you can write it as dx. If we use Leibniz notation, It's just the same thing. It's just that we write f prime x in terms of dy dx. So L equals to integral from a to b square root of 1 plus dy dx squared dx. Okay, so this is our arc length function. Okay, so we have derived the arc length function L equals to integration from a to b 1 plus dy dx squared dx. Let's say if the curve is written as a function of y, i.e. X is a function of y, then and where the limit now is between y equals to c and y equals to d, and the assuming or not assuming, given that g prime y is continuous, then we can write the formula for arc length from c to d. This time the limit is in terms of y, so 1 plus dx dy squared and dx, or in terms of g prime y, we can write down this as integral of c to d 1 plus g prime y, everything is squared there, and dx. So this is your arc length function if your graph is given like this. Okay, let's say, so here is c, here is d, so this graph here is x equals to g as a function of y. So yeah, you can convert it into this formula. Okay, let's do an example for the arc length. Okay, example 1, you can see from your slides or from your note, find the length of the arc of a semi-cubical parabola y squared equals to x cubed between the points 1, 1 and point 4, 8. So this is your P1 and P0, this is your Pn. Okay. First of all, you can try to visualize this graph. You can try to do it on a calculator, graphing calculator available on the internet, or you can do it in Excel if you want. Or if you have a graphing calculator, it would be even quicker. So this curve actually have two sides, lies on the two sides of the x-axis and y-axis, of course. But then from the limits given, 1, 1 and 4, 8, it's only here. Okay, so this is 1, 1, so 1, 1, and this is 4 and 8. So the limit is of this curve in this graph, the arc length is from this point only. Okay, 1, 1, 2, 4, 8. Thus we just need to find the length. Okay, so what do we do now? So we write down the formula. The arc length formula is given as L equals to integral from a to b 1 plus dy dx, everything squared and everything square root with respect to x. Okay, so first of all, we want to find the f prime x, or the dy dx. So you're given the y2 equals to x cubed, so y equal to x 3 over 2. So this one you will get dy dx. So dy dx here equal to 3 over 2 x 1 over 2. Okay, so what about dy dx squared? That will give you 9 over 4 x. Okay, so you put this inside the formula. So you have L equal to, the limit here is from a to b. A is 1, so 1 to 4, and square root of 1 plus 9 over 4 x dx. So I guess you can do this one. You can, if you want, you can pause the video and try to attempt it yourself. Otherwise, we'll just proceed. So you can use this u substitution, where u equal to 1 plus 9 over 4x. Then this will give you du equal to 9 over 4 dx. That's dx equal to 4 over 9 du. Then at the same time, you need to also change the limits if you were to use substitution, because this one here in the original integral is x equal to 1 and x equals to 4. So if you want to change the limit, change the integral in terms of u, then you've got to change, let's say when x equals to 1, then u equals to 1 plus 9 over 4, 1. That will give you 13 over 4. And when x equals to 4, u equals to 1 plus 9 over 4 times 4, that will give you 10. Then you can continue the integration in terms of u with the new limit. Okay, continue the integration in terms of the new limits. You have L equal to, so you know dx equals to 4 over 9 du, so you can put 4 over 9 outside. Now u equals to 13 over 4 until u equals to 10, and just the square root of u really, du. So 4 over 9, integrate the square root of u, you will get u 3 over 2 over 3 over 2, and then insert the limit from 13 over 4 until 10. Then you can you just do the integration, and you have this 13 over 4 to the power of 3 over 2. Oops, sorry, it's 10 first. Okay, it's 10, 3 over 2 minus 13 over 4 to the power of 3 over 2. Well, you do this on your own. You will get, so this will give you 8 over 27, and then 10 minus 13. Oops, what do I do here? 13 over 8 set 13, and finally you will end up with just 1 over 27 times 80 set 10 minus 13 set 13. Well, you can further simplify the answers into decimal places if you want, or you can just stop here. Okay, so that's it. You have found the length of the curve from point 11 until point 48 with using the arc length formula that we have just derived. Okay, still under the subtopic of arc length, but now our second application is the arc length function instead of arc length formula. So what is the difference between arc length function and arc length formula? So previously, when we derived the arc length formula, so we get this L equals to A to B, and then the square root of 1 plus f of f prime x, everything squared, dx. So this is a formula. Okay, this is a formula. This is not a function, because if you say something is a function, then it must have a variable. But when you put in the limit of a and b, it becomes a definite. It has a value. It has a final number. So it's not a function. So when we say that we want to determine the arc length function instead, so the function measures arc length of a curve from a particular starting point to any other point on the curve. So let's start with the definition of the arc length function as s. Okay, s as a function of x in this case. So we want to start with a starting point. So a here is any starting point. So a is a value, it's not a variable, but we want to stop at any value of x. We don't want to have a definite number like what we have in this formula previously. So we just want to put any variable x there. So we put the same formula inside, but we want to convert it into a function. So f prime, in this case we don't want to use x, we want to use another variable so as not to confuse what is x. Is it a limit or is it a variable? So in this case we put t as the variable. Then we have to integrate this thing in terms of the variable t, so dt. So we just replace the variable of integration to t so that x does not have two meanings. In this case, x here is the limit instead of the function, or instead of the variable inside the integral. Okay, so here dx equal to 1 plus f prime t. Okay, this one you know. I mean, if this is the from x, if you differentiate, then you get the opposite of integral, then you just get the inside function. Okay, and you can also write dx equal to, or just ds here, equal to 1 plus dx squared, not ds, it's dy. Okay, y dx squared dx. Okay, from here you can try to expand the inside of this third here. Okay, you can okay, let's just do that. Okay, dx squared plus dy squared dx squared. So then you will, when you take out the square root from the denominator here, you will end up with ds equal to dx squared plus dy squared. Okay, without the dx outside because it has been crossed out. So you can get ds equal to, and square everything, you have this plus this. So what do you get from this formula is that, well, if you have this curve here, this is your y, this is your x, and this is your curve. So if you have this tangent, okay, then so this is your delta y, this is your delta x, or dx, dy. So this will give you the ds, okay, the delta s. So this will give you that formula. So we're going to use this this thing here, okay, to derive the arc length function given any function with a starting point. Let's do that in the example. Alright, so example 2, we want to determine the arc length function given a function and a starting point. So in this case, let's find the arc length function for the curve y equals to x squared minus 1 over ln x, taking point p0, 1, 1 as the starting point. So this is our starting point, x equal to 1 until whatever value of x. So we want to have that function where x is the variable. And secondly, what would be the arc length along the curve from p0, 1, 1 to p1, where 3 and function of 3. Okay, so these are the steps that you should follow. First thing is to use the arc length generic function, where s of x equal to the integral from a to x, square root of 1 plus f prime t squared dt. So a, in this case, our a is equal to 1. X, just leave it at x. And then we just put everything in terms of t after this. Then to obtain the required arc length function specific to this curve. And secondly, we want to address the second part of the question. We want to determine the value for the length of the curve between the two given points. So just put in the limit from 1 to 3. Okay, so let's write down the function again. Y equals to x squared minus 1 over 8 ln x. From starting point is p0, 1, 1. Then, and the formula is s of x equal to integral from a to x, square root of 1 plus f prime t, everything squared, dt. So here, from here, we are given the fx, y as a function of x, equal to x squared minus 1 over 8 ln x. So just to avoid confusion, let's write everything in terms of t. So f of t is equal to t squared minus 1 over 8 ln t. Then f prime t equal to 2t minus 1 over 8t. Then what would be the 1 plus f prime t square? That would be 1 plus 2t minus 1 over 8t, everything squared. So you want to expand that. 1 plus 4t squared minus 1 over 2 plus 1 over 64t squared. And I'm going to continue there. Then equal to 4t squared plus 1 over 64t squared plus 1 over 2, and you can factorize this to get 2t plus 1 over 8t, everything squared. So this is your 1 plus f prime t squared, the inside term of the square root. So we're gonna put this inside there. Okay, so s of x equal to limits from 1 to x, 2t plus 1 over 8t, everything squared, dt. Then you, just expand this. Square root of something squared equals to that something. Okay, so just put it, that something, and integrate it. So you got t squared plus 1 over 8, oops, sorry about the t, okay, ln t, and then put in the limit from 1 to x. So you have x squared plus 1 over 8 ln x minus 1 squared plus 1 over 8 ln 1. Then you know ln 1 is just 0. So you have, at the end of the day, you have this as your arc length function. Okay, so the arc length function from starting point 1, 1 to anything, any value of x is given here, where this is your arc length function for that original y equal to x squared minus 1 over 8 ln x. Okay, starting from 1, 1 until any point n x something, x fx. Okay, so the second part of the question is to find the arc length value from p0 1, 1 until p1 3 and f of 3. So substitute the value into the formula. So you have this arc length function just now. So when x equals to 3, just put as x equals to 3 and put it in the numbers. Then you get this value.